Hi everybody, Physics Ninja. Today we've got a great problem dealing with a one-dimensional collision between two blocks. Except to make things a little bit more complicated, what we've added now is we've added a spring. It's connected to one of the blocks. All right, this is kind of a standard textbook problem from collisions, from momentum, and also involving different types of energies, right? You can have kinetic energy of the blocks initially, and then once they collide and that spring starts to compress, I can also have some spring potential energy, right? Into the system. So we're going to look at several different problems. I've got them listed here. We'll go through them in just a second. But again, with all my videos, if you like it, hey, give it a thumbs up. Consider subscribing to my channel. And if you don't understand something, ask a question, leave it in the comments section, and I'm going to try to get back to you as quickly as possible. Okay, let's look at the problems we're going to look at today. All right, so these are the four problems I want to look at. They deal with kind of various different questions, but let's just have a look at them. So I've got the two blocks coming toward each other, and I'm going to give you all of the initial information. Okay, I've given you the initial velocity of each block and also the mass of the blocks. I've also given you that spring constant that is connected to the block M2. All right, and the first problem I want to say, well, what happens after the collision? So that's the initial value, right? They're coming in like this. Yeah, that spring's going to compress, and then they're eventually going to release from each other. The spring will decompress, and after a long period of time, after the collision, what is the final velocity of each block? All right, so how would you solve that problem? Question B says, well, what happens at the instant when the speed of block number 1 is 3? If you look at the initial velocity up here, the initial velocity was 4, right? When it's actually during the collision, it might at some point be 3 meters per second during the collision. So at that specific moment, how would you find the speed of the other block, the block M2? Okay, so how would you set up the equation? Which one would you use? Question C says, determine the distance that the spring is compressed for this specific case. For the case we're just going to look at in part B, right? How far is the actual spring compressed in that case? And the last question, which is probably the most important that you really understand, is how would you find the maximum compression that this spring compresses during the collision, right? Which equation would you use and why would you use that equation? All right, so let's go and solve all of these four problems. We'll set up the equations and get to the solution for each one. All right, let's go. All right, in order to analyze the first part, let's find the velocity after the collision. The key to this is that after the collision, the blocks are no longer touching each other. Right? They're basically moving in whatever direction they're going to move, and the physics is going to tell us which direction they're going to move. But after the collision, there is no more energy in that spring because the spring is no longer compressed. Okay? So all we have here is a 1D collision. Okay? During the collision, there is energy put into that spring, right? But spring potential energy is that energy is conserved. Okay, whatever energy gets put into the spring, once the spring releases, all of that energy goes back into kinetic energy of the blocks. Okay, so this is really nothing more than a one-dimensional collision, and where we have two things. We're going to have conservation of linear momentum. So let's start with this, right? So momentum before and after. Okay, so momentum before is right here. All right, we're going to have the block M1 moving at some initial velocity. This is a vector plus the block M2 moving at some initial velocity. And then after, it's the final picture over here. So we have to find, well, M1 is going to have some final velocity, and M2 is also going to have some final velocity. Okay. So that's the momentum equation, and we have to solve for two unknowns. The unknowns are the final velocities of each block. But we need another equation. We have two unknowns. The other equation will be that the kinetic energy before and after is also going to be conserved. And why is that? Again, because the spring is no longer compressed. There is no more energy in that spring. Because we are comparing this picture to this picture. The only energies involved are kinetic energies. Okay, we're not dissipating any energy. There is no friction in this problem. It's only spring potential energy, and that gets put back. So our equation for kinetic energy before, again, 1/2 mv² for block 1, and 1/2 mv squared for block 2, and then that has to be equal to, well, again, 1/2 m1 v1 final squared, and then the kinetic energy of block number 2 after the collision. Let me write that down. All right, so these are the two equations that we have to solve. Now, it's a little bit tedious in order to solve that, okay? I did this in a previous video, and I am going to link the video in the comments section. You can go and have a look at this. For now, we're just going to write what the final answer that I obtained in that previous video, okay? And then we're going to plug in our numbers in order to find the final velocities. So go visit that video if you want to know how to get to these final answers. All right, so here are my two solutions that I obtained from my previous video. Okay, equation 1 and equation 2. Equation 1 is the final velocity of block M1. Equation 2 is the final velocity of block M2. Okay, and all we have to do here is substitute in the masses. Now it's kind of complicated. You have to be a little bit careful we don't make mistakes. But we have the masses given up here, and we also have the initial velocities, right? Now the only thing you really have to be careful is, and I'll do it for the first case right here. So let's go ahead and substitute our masses. M1 minus M2, so we would have 1.75 minus the block M2 is 2.3. over, and then I just add them up, okay? So plus 2.3. All right, now for the initial velocity I have 4, okay? And it's really this guy, right? This is 4.0 meters per second. It's moving to the right, okay? So when I substitute things over here, I'm gonna put positive 4 for my initial velocity. What I am doing right here is I'm going to assume that everything moving this way is going to have a positive velocity. Everything moving to the left is going to have a negative value for velocity. Okay, and this is important when you substitute in the values of v's inside these equations. All right, we still have one more term we have to be careful of here. We have the second term, so we have 2 times the mass m2, which again was 2.3, and divided by the same term here, right? 1.75 plus 2.3. Okay. The last thing I need to do is I need to multiply by the initial velocity of block number 2. It is listed here as 2.2, but keep in mind, it is moving in a different direction. So actually what you have to do here is you have to put negative 2.2 inside my equation, okay? Otherwise, it's not going to work out. Now you proceed with this, and at the end of the day, if I substitute in all the numbers correctly here, what you should find is a negative 3.04 meters per second. And this one here was my final velocity of block number 1. Okay. If I do the same thing for block number 2, what I'm going to end up finding here is a slightly different number. I get a positive number of 3.16 meters per second. Okay, so this is V2 final. So I have a look at these numbers. What does this mean? Well, it says, first of all, that V1 has a negative value. Negative value simply means that after the collision, the block is moving in the negative direction, which is to the left, right? That's how I've defined it right here. Block number 2 after the collision was a positive value, right? Positive velocities mean that it's moving to the right. Okay, so this is kind of the first part. This is how you would find the velocities after the collision, okay? This is a 1D collision where we have conservation of momentum, and since we have no more energy in the spring, the energy was put back, we have conservation of kinetic energy before and after. All right, we're going to now look at the instant here when we have a little bit of spring compression, and we want to know what is the velocity of block number 2 over here if I'm telling you that block number 1 is moving at 3 meters per second. Right? We just calculated that, so this would just be like at the beginning, right? Because we just saw that after the collision, block number 1 was moving to the left at like 3 meters per second. So this is really, it's still moving to the right at 3 meters per second. It's just slowed down a little bit, right? It started off right here at 4, and it's now moving at 3, right? So it's slowed down a little bit, but what is the final velocity of block number 2? Okay, so which equation we would use? Okay, so at this instant, really all we can do here is really conservation of momentum, okay? Because I don't know how much energy is in the spring, right? I don't have enough information in order to find how much energy is in the spring. I would have to calculate, right? Somebody would have to tell me, but I do have all the momentum information, right? So this is all I can do right here. I can do that the initial momentum of the system, it's written as like something like this, m2 V2 initial. And this here would have to be equal to M1 V1 final. In this case, I know V1 final. I'm telling you, it's at the instant when this is 3. Okay, and plus M2 V2 final. Okay, so we have to substitute our numbers, and really the only thing we're trying to solve for is this guy right here. We know everything else in this problem. So let's go ahead and just rewrite an algebraic expression for V2 final. Okay, so V2 final is M1 V1 initial plus M2 V2 initial. Now I have to bring this whole term on the other side, so it becomes negative V1 final, and at the end I need to divide by the mass M2. All right, now we plug and chug our numbers, okay? Try not to make a mistake here, right? So we're gonna have the mass M1 is 1.75, right? All of the information is given out here in this orange box. My initial velocity is +4, okay? What else? Plus the mass is 2.3 for M2. The initial velocity is, again, the magnitude is 2.2. However, I have to put negative 2.2 because I'm dealing with a momentum equation and direction matters. All right, minus. What do we have now? M1 is still our 1.75. Now, what do we do with this final velocity over here? Well, this is going to be +3. Right, we have a positive number because it is still moving to the right, okay? So that is a positive velocity. At the end, what we have to do is we have to divide this whole thing by the mass of M2, which is 2.3. All right, if you are careful and you put everything in the calculator, you should find that it is, at this instant in time, I got minus 1.44 meters per second. Okay, so the important part here is that at this specific moment, this guy is still moving, right? Let's just write this, moving. Which direction would it be moving? It's still moving to the left, okay? Because of the negative sign there. So we actually did have the correct arrow here, but I didn't know that when I drew the cartoon. All right, let's look at the next question, question C, where we're going to determine how far the spring is compressed when block 2 is moving at this velocity and block 1 is moving at 3 meters per second. All right, so for question C, how far is the spring compressed when we have block 1 moving at 3 and block 2 moving to the left at 1.44 meters per second? Okay, so this here is a problem of conservation of mechanical energy. Let me just write this down. So all we have here is two types of energies involved in the system, right? There is no dissipative forces in this problem. There's no friction between the blocks and the ground. So that means initially what we have is some kinetic energy for block number 1. I'll write this as K1 initial, plus what? Well, the initial energy of block number 2, plus, well, is there any spring potential energy initially? There isn't. I'll just write it, but again, keep in mind this guy here is simply equal to 0 because the spring's not compressed before the collision. What we do have now is during this collision, right? This happens during the collision because the blocks are slowing down. What we do have now is, well, we're going to have a little bit less kinetic energy for each block. So this is going to be K1 final plus K2 final. Well, guess what? If we don't have these numbers equal to the same, it's because we've stored some energy in the spring. And this is how we're going to introduce the spring compression at this specific instant. So let's go ahead and write this out a little bit further. So now we simply write down our terms. V1 initial squared plus 1/2 M2 V2 initial squared. This is kind of tedious, I agree, but you just got to get it done. V1 final squared plus 1/2. A lot of different terms. My arm is getting sore just writing this equation. Now the spring potential energy. This one you should remember. It's 1/2 K and X squared. X is the amount of compression, and that is really what we're looking for. Well, guess what? I can cancel out all of the 1/2 terms. They're in every single term, so you can multiply both sides by 2 just to get rid of those. And all we're really looking for now at the end of the day is we're going to solve for X. So you can simply bring the kinetic energy terms on the other side, and then divide by the spring constant, and you can get kind of a complicated looking expression. I'm just going to write it down. Okay, so let me group some of the terms. My algebra is pretty good. I think I can do this. Mine is V1 final squared. I'm going to group the terms with M1. All right. Let me look at the terms now with M2. There should be two of them. There's the initial velocity squared term, and then there's going to be the final velocity squared term. Now at the end, I'll probably need to divide by the spring constant, which I've also given you. So for this problem, we have 500 newtons per meter. Now at the end, remember, I have to take the square root because my energy equation is x squared. So I need to do that. All right. Now we have to plug in all of our numbers into this complicated looking expression, but that is easy to do. And I'm going to leave that to you, the user or the YouTube video watcher. Have fun with that one. I'll tell you what I did and what I got at the end, and I was really careful. I probably did it 2 times because I don't want to do a mistake. 0.193 meters, or you can kind of just write that as 19.3 centimeters is the amount of compression I'm going to get when block number 1 is moving at 3 and block number 2 is moving to the left at 1.44. All right, let's look at our final problem. All right, the last question I want to do today is, what is the maximum compression of the spring? And again, this here clearly has to happen during the collision, right? So we know all the values initially. Now, how do you find the maximum compression? In the previous case, I looked at a case which was during the compression, but how would you find the maximum compression? Okay, and the key to this problem here is right here in my figure, is that at the maximum compression, you may have to think about this for a while, is that both blocks are going to be moving at the same speed. Okay, and this is really, really the key to this problem. This simplifies our momentum equation, right? Because at that instant in time when it's maximum compressed, they're moving at the same speed. Okay, so what we're going to do then is write down our momentum equation. Okay, momentum equation then at that specific instant is, again, we should be getting used to this one, m2 v2 initial. Now the simplification comes on the right-hand side here. At this point, since they're moving at the same speed, you basically have this whole chunk of stuff, M1 and M2 combined, and everything is moving together at some common final velocity. So this allows us right away to find the final velocity of the system. Okay, so I'm just going to do a little bit of algebra here just to rewrite my equation. And at the end here, it's simplified because I simply divide by the total mass, M1 plus M2. All right, we're going to substitute our numbers. Again, 1.75 for that, positive 4 for that velocity, plus 2.3 was the mass of block number 2. Its velocity was to the left, so I put a negative sign there. And at the end, we get 1.75 plus 2.3. Okay, so my final speed at the maximum compression for this problem is 0.48 meters per second. Now, one thing we notice right away about this answer is that it is a positive value, right? Since it's positive, guess what? This means it is moving to the right, okay? And it's going to move to the right because initially what we had was this block had more momentum than that block. If you do the multiplication here, you're going to find that that's a positive value. That's, a little bit less than 8, and this one here is not quite as big. So block number 1 had more momentum, which means that after the collision, at this specific point, things are going to move to the right. Okay, so now that we know the final speed, we are in a better position now to find what is the maximum compression of the spring. All we have to do now is go to our energy equation and solve for this. So let's go ahead and do that. All right, so to find the maximum compression, now we're going to go back to our energy equation. Again, we have conservation of mechanical energy. And our statement of conservation of mechanical energy looks like this. Initially all we have is kinetic energy again. And now what we have at the maximum compression is we're going to have some final kinetic energy of the entire system here. And we also have some spring, right? Not only kinetic, but we also have some spring because the spring is compressed. Now we go ahead and start substituting our variables. Kinetic energy, always the same. All right, now what about this term, the final kinetic energy, or the kinetic energy at this instant in time? We just solved what the speed was, or the velocity. So now all we have to do is, it's 1/2, and the mass of everything is simply the mass of both blocks. And our final speed is this one, so final speed squared. Okay, so that's the final kinetic energy. And at that specific instant, we have some spring potential energy. And that's 1/2 kx, and here I'm going to even write a maximum value here. Okay, so this is what conservation of mechanical energy looks like. The only unknown in my problem right now is going to be whatever this x max is. So let's go ahead and just do a little bit of algebra again. Same thing as what we previously did. Get rid of those 1/2 factors. All we want to do is solve for x. So we do a little bit more algebra. And let me just go ahead and write it. X max should look something like this. There's going to be a big square root, but I'll put that one at the end. Squared. The next term was this guy, m2v2 initial squared, which again, everything is given here in this orange box. I have to bring this kinetic energy term on the other side, so that becomes negative m1 plus m2, v final, okay? And now divide by that spring constant, right? Because that ends up multiplying x max squared. Okay, and at the end, you have to take the root of everything. Ooh. All right, so that is our messy looking expression. However, we know every single quantity in this term. K is 500 newtons per meter. We know all the initial values. We know the final value we calculated here is 0.48. Put in all the numbers. If I did that correctly, I get 0.276 meters. Again, that is equivalent to 27.6 centimeters. All right, folks, that's it. So 27.6 maximum compression. Anyway, hopefully you appreciated this video. Hopefully you learned something. Remember, at the maximum compression, everything is going to be moving together as one big block. Okay, thanks for watching. We'll see you next time. Bye-bye.